Rankine vapor power cycle or ideal vapor power cycle. This is the thermodynamic cycle taken as the standard ideal cycle for the comparison of all the steam power plants generating electric power. Here the working fluid is steam or H2O, which is changing its phase. In all the previous cycles what we have discussed, that is in the gas power cycles, the working fluid is assumed as mostly air, which is an ideal gas with constant specific heats Cp and Cv. But here the working fluid is steam, which is changing its phase into water, and again the water being converted into the vapor for doing work in the turbine, which is not an ideal gas. So the cycle could be seen on the flow diagram like this. There are basically four components in the cycle, namely boiler, also known as a steam generator, then steam turbine, the very important prime mover in the mechanical engineering. Then we have condenser, which is nothing but a heat exchanger, followed by P for pump. This is the flow diagram for a simple ideal Rankine vapor power cycle. The states are marked as the state of the steam, that is high pressure, high temperature steam leaving the boiler is indicated by 1. The low pressure, low temperature exhaust steam leaving the turbine is indicated by state 2. The condensate liquid leaving the condenser is indicated by state 3, and the water entering the boiler, the feed water entering the boiler is indicated by state 4. If you look at the cycle, there is feed water entering the boiler. In the boiler, what are the main parts? We have the boiler drum, we have the boiler furnace. Into the boiler furnace, the fuel is fed. Mostly the fuel would be coal. Of course, there are oil-fired boilers are also there, but in the conventional thermal power plants, the fuel is usually coal, pulverized coal. And air is fed into the boiler furnace for combustion of the coal. The heat generated due to the combustion of the coal with the help of oxygen present in the air, or the calorific value of the fuel liberated in the boiler furnace, is carried by the hot flue gases generated in the boiler furnace. These flue gases flow through the boiler drum, where they transfer their heat to the feed water passing or circulating through the boiler tubes. Due to this heat transfer, the feed water changes its phase into steam and also becomes superheated. So there is high pressure, high temperature, superheated steam generated in the boiler. This steam generated in the boiler at state 1 now enters the turbine, steam turbine. Steam turbine is another important thermal turbo machine in which high pressure steam expands from boiler pressure to the condenser pressure isoentropically, that is reversible and adiabatically, through a very high pressure ratio. The low pressure, low temperature steam leaving the turbine after doing work shall enter the condenser. Into the condenser we shall supply cooling water to pick up the heat from the condensing steam. The water after picking up heat will go out. The steam condenses at very low pressure in the condenser. So we get condensate liquid water. The steam condenses into saturated liquid. This saturated liquid is also known as condensate liquid water, which is at condenser pressure. This water is pumped from very low condenser pressure to very high pressure in the pump, which requires mechanical work input. This mechanical work input to the pump may be extracted from the turbine. This cycle could be represented on temperature entropy plane like this. The cycle in total has 4 processes, namely 1 to 2, expansion of steam in the turbine, isoentropic expansion it is, or reversible adiabatic expansion, and 2 to 3 is isobaric or constant pressure heat rejection in the condenser from the steam to the condenser cooling water. 3 to 4 is isoentropic pumping of feed water from the condenser pressure to the boiler pressure. 4 to 1 is heating of water, change of phase of water, and then superheating of steam in the boiler, generating high pressure, high temperature, superheated steam. So the cycle has 4 processes, namely number 1, 4 to 1 is isobaric, that is constant pressure, heat supply to feed water, converting it into high pressure, high temperature, superheated steam. This is done at boiler pressure, which is very high, in the range of 100 bar 150 bar, 250 bar, sometimes even at a pressure more than critical pressure of steam. Process 1 to 2 is reversible adiabatic or isoentropic expansion of steam from boiler pressure to condenser pressure in the turbine doing mechanical work. Then process 2 to 3 is isobaric or constant pressure heat rejection from exhaust steam leaving the turbine to condenser cooling water circulated in the condenser bank of tubes, during which the steam condenses into saturated liquid at condenser pressure. Then the process 3 to 4 is isoentropic pumping of water, saturated liquid water, leaving the condenser from condenser pressure to boiler pressure, and then feeding that water into the boiler for heat supply. Usually the condenser pressure of steam, that is absolute pressure, in the condenser is 0.1 bar or 10 kilopascal. The boiler pressures employed in a Rankine cycle may have wide range, that is from 35 bar to 200 bar. Sometimes the steam is generated even at the range of critical pressure of steam, that is 221 bar. There are supercritical boilers which could generate steam even in the range of critical pressure of steam. For example, Benson boiler is a once through drumless boiler with a radiation superheater that it could generate steam in the critical pressure range of steam, that is in the range of 2 to 121 bar. That is, among all the thermodynamic cycles what we have seen, the pressure ratios are maximum in the Rankine cycle, because even if we assume that boiler pressure is 100 bar, whereas the condenser pressure is 0.1 bar, the boiler pressure divided by the condenser pressure will be 100 by 0.1, that is around 1000. So the highest pressure ratios could be encountered in the Rankine vapor power cycle as compared to the other thermodynamic cycles, whereas in the Brayton cycle or a gas turbine cycle or a Joule cycle, the pressure ratios are hardly 6, 7 or 8 as we have seen in the previous problems. So that is what the difference between other cycles and the Rankine vapor power cycle. In fact, this is the cycle used for around 70% of the electric power generation in India. Now let us see the thermal efficiency of ideal Rankine cycle. Let us draw this cycle on the temperature entropy diagram. One to 2 is expansion in the turbine, 3 to 4 is pumping of water where work is needed, 4 to 1 is heat supply in a boiler to feed water, converting it to the high pressure, high temperature SH steam, means superheated steam. The steam expands down to condenser pressure from boiler pressure. Here BP means boiler pressure, which is in the range of 100 bar or 150 bar or 200 bar. CP means condenser pressure, which is in the range of 0.1 bar, nearly 0.1 bar or 10 kilopascal. Great vacuums are maintained in the condenser. For that matter, there is a great vacuums are maintained in the condenser. Approximately 65 centimeters of mercury vacuums are maintained in the condenser of steam power plant. If you look at the 4 components, that is boiler, turbine, condenser and pump, all are steady flow machineries. If you apply the steady flow energy equation for turbine, that is steam turbine, steam is entering it with an enthalpy of H1. Steam is leaving the turbine with an enthalpy of H2. Therefore, neglecting heat transfer, because heat is not rejected from the turbine to the steam turbine to the surroundings. Q is 0. Therefore, Q minus W is equal to delta H plus delta KE plus delta PE, which is steady flow energy equation. Q is 0. Neglecting KE and PE changes of steam in the turbine, the work output of the turbine is H1 minus H2 kilojoule per kg, where H1 is equal to enthalpy of superheated steam at boiler pressure and superheat temperature entering the turbine, and H2 is enthalpy of wet steam, because point 2 is in the wet region of the TS plane. H2 is enthalpy of wet steam leaving a turbine, which could be calculated as HF plus X2 into HFG. Previously we have discussed about how to calculate enthalpy of wet steam. All this is to be calculated at condenser pressure, where X2 is the, what is X2? Dryness fraction of exhaust steam. Now, writing the steady flow energy equation for boiler or a steam generator. Into the boiler, what is fed from the outside is feed water at an enthalpy of H4. What is generated in the boiler is high pressure, high temperature, superheated steam at an enthalpy of H1. This is only for the boiler piping I am writing, not for the boiler furnace. Therefore, the heat supplied to feed water at constant pressure or boiler pressure is equal to H1 minus H4 kilojoule per kg. Since work done in the boiler is 0, change in Ke is 0, change in potential energy of water is also 0. There is only heat supplied from the hot flue gases generated in the boiler furnace to the feed water. Therefore, heat supplied is delta H of feed water. Now, applying SFE to pump. Pump is a steady flow device which receives water, feed water, at enthalpy of H3 and increasing its pressure to boiler pressure, and exit enthalpy is H4, and there is mechanical work required for the pumping. Q is 0. Therefore, from SFEE we can write that work input to pump is equal to change in enthalpy of feed water across the pump, that is H4 minus H3 kilojoule per kg. Since pump is a steady flow open system, we know that work done in a steady flow reversible process is given as minus integral VdP. Hence, work done in the pump is integral VdP from condenser pressure to boiler pressure. Since V is constant for water, which is equal to 0.001 meter cube per kg, because water is incompressible fluid, work of pumping can be calculated as V of the water, feed water, into boiler pressure minus condenser pressure. Kilojoule per kg. The pump work, what we had calculated as H4 minus H3 is far lesser than work of turbine. That is the reason why, that is many a times pump work may be neglected. Approximately 5% of turbine work is consumed for driving pump. Pump work is very small as compared to the turbine work. That is the bottom line. And heat rejected in the condenser at constant pressure or condenser pressure is equal to change in enthalpy in condenser, that is H2 minus H3 kilojoule per kg of steam, where H3 is equal to enthalpy of saturated liquid water at condenser pressure. After condensation, the steam becomes saturated liquid, that is HF at Cp, that is condenser pressure. Hence, thermal efficiency of ideal Rankine cycle or vapor power cycle can be calculated as net work done per cycle divided by heat supplied. Net work done per cycle is Wt minus Wp, because a part of turbine work, though it is lesser, a part of turbine work is used to drive the pump, divided by heat supplied in boiler, which is written as H1 minus H2, that is turbine work, minus H4 minus H3, that is the pump work, divided by H1 minus H4, that is heat supplied in the boiler. Usually, the thermal efficiency of Rankine cycles, when the cycle is operating in the normal working ranges generally employed, we get around 35% to 40% of thermal efficiency for a simple ideal Rankine cycle. Approximately the thermal efficiency shall be equal to the 35%. Now let us see how to calculate the thermal efficiency of the Rankine cycle. Let us consider the cycle on TS plane. Neglecting pump work because it is very low, H3 can be approximately made equal to that of H4 because H4 minus H3 is work of pump. When pump work is very minimum, then H4 is almost equal to the H3. Then thermal efficiency of the ideal Rankine cycle can be written as H1 minus H2, that is work of turbine divided by heat supplied in boiler. It can be written as H1 minus H2 divided by H1 minus H3, assuming that H3 is almost equal to the H4 because pump work is very low. H1 is enthalpy of the superheated steam at boiler pressure and superheat temperature of T1, which is obtained from the steam tables, because once the boiler pressure is known and superheat temperature is known, we can easily read the enthalpy from the steam tables. And H3 is equal to HF, or liquid enthalpy, saturated liquid enthalpy at condenser pressure, that is also read from steam tables. Just similar to superheat enthalpy is taken from superheat tables. Now coming to the H2. H2 is in the wet region. Point 2 is in the wet region. Therefore, to get enthalpy at 2, we need dryness fraction at condenser pressure. Again, dryness fraction of steam leaving the turbine is needed to calculate enthalpy at state 2 H2. How to get dryness fraction? To get dryness fraction, we have to equate the entropies. S1 is S2 because 1 to 2 is expansion in the turbine, that is isoentropic expansion. S1 is enthalpy of the superheated steam at boiler pressure and temperature T1, which is read from the table, that is equal to S2 is the entropy of the wet steam at state 2, which is given as SF plus X2 into SFG at condenser pressure. In this equation, SU could be read from the table. SF at condenser pressure could be taken from the saturated water or saturated steam properties. SFG is also read in the saturated steam tables. The only unknown is dryness fraction of exit steam leaving turbine. That could be easily calculated from this equation. Please note that this dryness fraction X2 calculated should have to be more than 90% or 0.9 to avoid the erosion of turbine blades. If the moisture content is more than 10% or otherwise the dryness fraction of steam is less than 90%, during any part of expansion in the turbine, there is every likely chances that turbine blades are eroded. It is a physical action. If the moisture is more than 10%, these liquid particles may hit the turbine blades with a high velocity and may cause erosion of turbine blades. Having calculated dryness fraction of steam X2 leaving turbine, its enthalpy H2 could be calculated. Once this enthalpy is obtained, thermal efficiency of ideal Rankine cycle could be easily calculated as H1 minus H2 divided by H1 minus H3. Now, considering irreversibilities like friction in both the machines, that is pump and turbine, both are thermal turbo machineries, the actual Rankine cycle is represented on temperature entropy plane as this is the two-phase diagram of steam on TS plane. This is isoentropic expansion, heating of water, change of phase of water, superheating, and this is isoentropic expansion of steam in the turbine. If you take the frictional effects into account, the actual expansion of the steam in the turbine goes rightwards, generating entropy. 1 to 2 dash is isoentropic expansion, 1 to 2 is actual expansion. Similarly, 3 to 4 dash is isoentropic pumping of water, actual pumping of water is 3 to 4, taking the frictional effects into account in the machine. And 4 to 1 is heat supply in the boiler. So 1 to 2 dash is isoentropic expansion of steam in turbine, which is a vertical line. 1 to 2 is actual, that is irreversible adiabatic expansion, that is with friction. 3 to 4 dash is isoentropic pumping of water in the pump. 3 to 4 is actual pumping with friction in the pump, that is adiabatic with friction. 3 to 4 is adiabatic with friction, 3 to 4 dash is adiabatic without friction, that is isoentropic.